Alaikum guys, welcome. Okay, so in this lecture we are going to talk about 3D bond notation of covalent compounds. Okay, how the 3D representation, the three-dimensional representation of covalent bonds in your three-dimensional space. Okay, let's begin. This is a very important part because has been tested on the past papers quite a few times. So now, plane bond. First of all, this stick over here is representing a plane bond. Plane bond actually means a bond which is within the plane of the paper. It is not coming out at you, nor is it going into the plane of the paper, but rather it stays within the plane of the paper. Okay, this dotted bond over here is actually representing a bond that would go into the plane of the paper. For instance, if you are making carbon dotted hydrogen bond, this means that this carbon is right in front of you, but the hydrogen is going behind the carbon into this whiteboard, okay, or into your screen. Then comes wedge bond. This triangular wedge that you can see over here is, at times it is actually colored or shaded, but this triangular wedge over here, it represents a bond which is sticking out at you out of the plane of the paper. Okay, so it's basically a bond that is like this or like this or like that. Okay, but it is out of the plane of the paper. These are the three bonds which are there, and this was just a quick recap, okay, because you guys have already done this in your course. Now coming to the first example, methane gas. Or okay, so basically the shapes of molecules that we are going to study are actually derived on a theory which is known as the valence shell electron pair repulsion theory. Okay, valence shell electron pair repulsion theory, which is also called Vesper. Vesper theory states that the lone pair repulsion is the greatest, followed by the lone pair bond pair repulsion, and the bond pair repulsion is the least. What do I mean by that? Well, if for instance you have water molecule over here, let me just draw a small water molecule over here. Okay, this is a straight water molecule with its lone pair of oxygen on top of it. Remember, this was the sort of water molecule you used to make in your O levels. Now you've got two lone pairs on oxygen and you've got two bonded pairs over here. Now the valence shell electron pair repulsion theory states that these lone pairs over here, they'll of course repel one another, right? Because they are electrons, they are negatively charged, so they'll repel one another. But these bonded electrons are also negatively charged. They'll also repel those electrons, and they'll repel one another, and they'll also repel those electrons on top. But the valence shell electron pair repulsion theory says that the repulsion between these lone pairs is going to be the greatest, is going to be the strongest, and it will overcome the repulsion between the bonded pairs. As a result, what would happen? As a result, the shape of this molecule will change. It will get twisted because there will be a net force downwards. Why will it be downwards? It will be downwards because this oxygen, the lone pairs on the oxygen, they are actually applying a greater force as compared to the force which is applied between these two bonded electrons. So net force would be downwards, and the shape of oxygen would tilt, and the straight bond of oxygen that we have made, it will become bent. Okay, so this is what the valence shell electron pair repulsion theory is telling us, that due to the interaction between lone pairs, lone pair, bonded pair, and bonded pair, due to their interaction, the shape of the molecule changes. Okay, and this shape of water molecule is known as a bent shape according to that theory. It is also called non-linear shape because of course it's not linear. So non-linear, it's not in a straight line, and it is also called bent. It is also called V-shaped. It is also called angular. You may name it any way you wish. And this bond angle is also important. Okay, you must know the bond angle as well. This bond angle for water molecule is from 104 to 105 degrees. Okay, it has been measured to be 104.5 degrees, but yeah, 104 to 105 degrees for bent water molecules. All right, now, so this is the first shape that we did, water molecule. And if you look at it carefully, I have made two plane bonds. Plane bonds actually mean that these bonds are actually in the same plane. They are in the same line. Okay, I could have drawn a wedge and a dotted bond as well, because wedge and dotted bond are also in the same line, but the only difference would have been that the wedge would have been sticking out at you, and the dotted bond would have been going into the plane of the paper. So it would have been somewhat like this. Okay, look at these two markers. This marker is sticking out at you and the other marker is going away from you, and assume this hand of mine to be the oxygen molecule. Okay, but still if you look at their plane, the two bonds are in the same plane. See, you've just rotated this entire molecule like this. It's the same molecule. So you can draw it using two plane bonds, or you can draw the water molecule as a wedge and a dotted bond. Okay, hydrogen, hydrogen over here, and of course you have to draw the lone pairs. Now after this, this was the first shape. Okay, and this was according to this theory that the repulsion between the lone pairs is the greatest and bonded pairs is the least. We have derived the different shapes of different molecules. Let's begin to talk about them. Alright, so now the first molecule is methane over here. Carbon is bonded to a hydrogen, a hydrogen, a hydrogen and a hydrogen. 4 hydrogen atoms. The same carbon atom is bonded to 4 hydrogen atoms. Now if this carbon atom is bonded to this hydrogen atom on top and to this hydrogen atom over here, I have drawn both the bonds by plane. I have shown both the bonds to be plane bonds. This means that both of those two bonds are in the same plane, right? They are within the plane of this board or within the plane of your paper. And this bond over here is a dotted bond. Dotted bond means that this bond is going into the plane of the paper, so it's going away from you into the plane. It's going behind the board into the, it's basically passing through the board. And this wedge is actually sticking out at you outside the board, because we have to think of it to be in 3 dimensions. Okay, so the wedge is sticking out at you, the dotted bond is going into the plane, and these two are within the board, within the whiteboard, as you can see all the other stuff within the plane of the whiteboard. So this is how methane molecule looks like. So any molecule which has 4 bonded pairs, only 4 bonded pairs, no lone pairs on the central atom, that molecule will have a shape called tetrahedral structure. Why tetrahedral? Tetrahedral because if you join all the hydrogen atoms by an imaginary line, meaning going here to here and then coming down and then going up in 3-dimensional space, they'll form a tetrahedron. Tetrahedron is a shape basically. Tetra means 4, so it has 4 faces actually. Okay, 3 on top and 1 at the base, 3 triangles on top and 1 triangle at the base. It's a pyramid basically. Okay, a triangle based pyramid is called a tetrahedron. So it's tetrahedral because it has a shape resembling to the triangle based pyramid. So, and the bond angle between each of these bonds is 109 degrees. Okay, so this was one example of methane molecule, right? But any molecule, by any I mean most of the molecules which have 4 bonded pairs and no lone pairs, and the bonded pairs must be single covalent bonds, then the shape of that particular molecule is going to be tetrahedral. Now for instance, I have this molecule CH3, CH3, and I'll ask you the shape of this carbon atom over here and that carbon atom, then what's going to be the shape? Basically, if you look at it carefully, this carbon atom on the left has 3 hydrogen atoms bonded to it, and the 4th bond is bonded to a carbon atom. Again, it has 4 single covalent bonds. 4 single covalent bonds means that it is also tetrahedral in shape. It also has a bond angle of 109 degrees. It's actually 109.5 degrees, but 109 degrees. Okay, you may find 109 written somewhere, and somewhere you might find 109.5 degrees. Both are acceptable. Okay, so this is how it changes. So whenever you have 4 single covalent bonds, all are bond pairs, no lone pairs involved, the shape is tetrahedral, bond angle is 109.5 or 109 degrees. Okay, examiner can ask you to draw the structure, to draw the shape in 3 dimensions. So how are you going to do that? You're going to draw 2 plane bonds, a dotted bond and a wedge, and that's it. Okay, and by the way, the positions, the placements of the dotted bond and the wedges can change. Okay, you can place a wedge over there and a dotted bond over here, or other way around. It's up to you, doesn't matter. Then comes the second shape. Actually, this should have been the first one. It's called linear. Why linear? The carbon atom over here has 2 double bonds and no lone pairs at all. If it doesn't have any lone pairs, this means that all are bonded pairs. Okay, both of them are bonded pairs. Bonded pairs means that the repulsion is going to be equal on both the sides. If they are equally repel one another, they'll try to go as far apart as possible. Over there, why wasn't it possible? Because we had 4 different bonds in different directions and different planes, right? Over here, why wasn't it possible over here? Because we had lone pairs, but over here we've only got two sets or two regions of electron densities, two double bonds basically, and both of them are identical to one another, so they'll try to go as far apart as possible from one another. This shape is called a linear shape. The bond angle over here is 180 degrees and it's within the plane of the paper, okay? It's 180 degrees. Why? Because it's straight line, right? A straight line is 180 degrees. Then comes, so carbon dioxide is 180 degrees linear. Then comes the third molecule, ammonia. In ammonia molecule, the nitrogen has one lone pair and it has three bonded pairs. So of course, the lone pair bonded pair repulsion is going to be greater than the bonded pair repulsion according to the Vesper theory. Now, there are three bonds, right? Out of the three bonds, two of them are within the same plane. Basically, one is sticking out at you, other is going behind the board, but both of them, if you look at their plane, they are in the same plane. But the third bond is out of the plane. It is in another plane. Okay, it is within the plane of this paper, and these two are either sticking out at you and going away from you. The bond angle in between each one of them is 107 degrees or 107.5 degrees. The shape is called trigonal pyramidal. Why pyramidal? Because this is a pyramid that has been made. Trigonal because it has three angles, 1, 2, and the third one is from behind, okay? It is between this dotted bond and this plane bond. Okay, this angle is also 107 degrees. And it's pyramidal because this is a pyramid. If you look at it carefully, if you join the hydrogens with one another, you've got the base of the pyramid. Okay, it's a pyramid shaped structure. So any structure that has one lone pair and three bonded pairs is going to be a pyramidal, trigonal pyramidal structure. One lone pair, three bonded pairs, according to the valence shell electron pair repulsion theory. Then coming to the fourth one. The fourth one is very easy. It's called trigonal planar. Planar means within the plane, within a single plane. So three angles which are within the same plane. If you look at this one carefully, there is this, and okay, if they are within the same plane and there are three angles, what does that mean? This means that if you join all the three angles, they'll form a circle, right? If you look at this structure over here, it has three bonded pairs and no lone pairs at all. If you look at this dotted bond is sticking at you. It's like this. The wedge is going in, the dotted bond is going into the plane and wedge is sticking out at you, and this bond is within the plane of this board, right? So now if you join all three of them together, you can bring them in a single plane, okay? And trigonal planar actually means a flat molecule. You can represent this using a bond, a dotted bond or a wedge, or you can represent it by using all three single bonds, all three plane bonds, okay? Because it's of course in the same plane. It's just moving around the molecule here and there. Okay, if you pull it out of this plane and you rotate it, so you can rotate it in different directions, but all the three will always be in the same plane. If you join all the three chlorine atoms, they'll always form a triangle, okay? Now, since their angles form a circle, this means, and all of these angles are equal, because it's a triangle, all of these are equal, so the bond angles are going to be, the total angle of a circle is 360 degrees, and there are three angles, so 360 divided by 3 is 120, so 120 degrees is the bond angle over here, okay? Whenever you have three bonded pairs, three single covalent bonds, or three regions of electron densities, by regions of electron density, you can also include the double bonds in there, okay? For example, in case of alkenes have a double bond and two single bonds. So again, you've got one region, second and third region, three regions of electron densities again. But over here, what's the difference? The difference is that you don't have any lone pair and you've got a double bond. Okay, so double bond, still it's gonna be a planar molecule. Okay, so whenever three regions of electron densities are present, double bonds are also a region of electron density, a single region of electron density, okay, because electrons are concentrated there. So 120 degrees is going to be the bond angle, three bonded pairs should be there and no lone pair should be there. Okay, so then it's going to be called a trigonal planar molecule. Then coming to PCl5, this molecule is very important. And by the way, this molecule, you can think of this molecule as a mixture of two previously spoken molecules, or two previous molecules that we've talked about. One is this one, trigonal planar. You pull it out and you place it here, okay, trigonal planar. And the second molecule that combines with this molecule forms that molecule. What's the second one? It's actually the linear molecule. What we actually do is, we take out this carbon dioxide molecule. This marker is representing carbon dioxide, okay, the two ends are representing oxygen and my fingers are representing carbon. Now we've taken out the carbon dioxide molecule, we rotate it by 90 degrees and place it on top of this bromine, okay, and when we do that, we get this molecule, okay. This is how the bonds are arranged, okay, meaning two bonds are going up and down perpendicular to the original three planar molecules, okay. So if these three chlorine atoms were already forming a plane, just like this molecule, the two molecules, the two carbon atoms which have been added, the two chlorine atoms which have been added on top of the phosphorus and beneath the phosphorus, they are going to be perpendicular to this original plane, okay. So you've got two types of angles in here. This angle between the chlorine on top and the chlorine on at the bottom, in between this bond and this chlorine atom over here, the third chlorine atom is going to be 90 degrees, and the angle between the original three chlorine atoms which were in this plane is going to be 120 degrees. Clear? Why is this 90 degrees? Because it's perpendicular to the plane in which the other three chlorine atoms are already present, okay. Or simple, just if you have 5 different bonded pairs and no lone pairs, then of course it's going to be this structure. This structure is called trigonal bipyramidal. Why pyramidal? Because it's called trigonal because again it will have three angles, and the three angles are in here in the plane, within the plane, these three angles. And bipyramidal because if you join in 3 dimensions, if you join this top chlorine with each of these chlorines, you'll get a pyramid on top. And if you do the same with the bottom chlorine, you'll get a pyramid at the bottom. So you'll get 2 pyramids actually joined together by a triangular base, okay. So whenever you have 5 bond pairs, you've got 2 angles, 120 and 90 degrees. Then coming to the last one, SF6. SF6 is a typical example of this last molecule. In this molecule, instead of having a triangular base, we've got a square base. Instead of having a triangular base, we have a square base, and the remaining structure stays the same. Meaning you've got a fluorine on top and at the bottom, just like these 2 chlorines, right? And you've got the 4 fluorine atoms, meaning 2 dotted bonds, 2 wedges. If you join the 4 fluorine atoms together, you'll get a square shaped molecule, a square. And if you join each of these fluorine atoms with the fluorine on top, you'll get a pyramid, a square base pyramid on top. And if you join the 4 fluorine atoms with the fluorine at the bottom, you'll again get a square base pyramid at the bottom. So this structure is called octahedral. Why octahedral? Because it has 8 faces. Why 8 faces? Because a square shaped pyramid on top means 4 faces. A square shaped pyramid at the bottom again means 4 faces. So 4 plus 4 is 8. Okay, so octahedral. And all angles, by all I mean all angles in here are 90 degrees. Okay, there's just one single angle in here, that is 90 degree. This molecule over here has 2 types of angles, 90 and 120 degrees. Trigonal bipyramidal has 2 angles. And the rest of them have single angles. So only this molecule has 2 different types of angles. So now, guys, a short trick of learning all of this stuff. What you guys should do is, you guys should just learn the molecule of a tetrahedral compound. Okay, tetrahedral means it has 4 bonds, 4 single covalent bonds, or 4 regions of electron densities. Now, and the bond angle is 109 degrees. Now, if any one of these 4 bonds is replaced by a lone pair, for every lone pair you subtract 2 degrees from its angle. Okay, now this is 109 degrees, right? If I remove a hydrogen from the top and replace it by a lone pair, what will the shape become? Won't it become ammonia? Meaning the shape of ammonia, it will become a pyramidal structure, right? Now, since it changed from tetrahedral to pyramidal, I'm going to subtract 2 from 109 because we've added 2 lone pairs over here now. So 109 minus 2 becomes 107 degrees, right? Now from here, if I replace another bond and make it 2 lone pairs and 2 bonded pairs, I have to remove another 2 degrees from the 107. And as soon as I do that, I get a shape of water molecule. 2 lone pairs, 2 bonded pairs, 105 degrees, right? And for this one, for the planar molecule, you have to learn this one. And it's easy, guys. It's 120 degrees because you've got 3 angles. Divide 360 by 3, you get 120, right? If over here, one of the bond is replaced by a lone pair, then what you'll need to do is you'll need to subtract from 120, not from 109 then, okay? If for instance you have some molecule, I'm just making this up, this is M, and there's a chlorine over here, this is another chlorine, and there is a lone pair on top, then what's going to be the angle? It's going to be 118, okay? They do give suggest type questions like these, okay? They give you a molecule and they ask you to predict the shape of this molecule, so this is how you're going to do that, okay? In case of alkenes, again, in case of alkenes, just count the regions of electron densities. If you look at this carbon atom over here, this one, how many regions of electron densities are there? A double bond, 1 and 2, 3. 3 regions of electron densities, 3 regions of electron densities are present in trigonal planar molecules. So this is again planar, the bond angle is going to be 120 degrees. Simple. For PCl5 and SF6 you will need to learn. Acha, now I'm just giving you a question for you guys to practice. PCl3, what do you guys think should be the shape of PCl3? Comment it in the comment section, okay? I'll try checking it. PCl3 has a phosphorus, 3 chlorine atoms, so 3 bonded pairs. The bonded pairs, let's make a dotted and a wedge. The chlorine, the chlorine, the chlorine, and phosphorus will have a lone pair because it's in group 5. Isn't it similar to ammonia? It is similar to ammonia, right? Or you can think of it this way. There are 4 regions of electron densities. 4 regions mean 109, but there is a lone pair. So 109 minus 2 is 107 degrees is going to be the bond angle over here. Right? So that's it, guys. Thank you so much.